Good morning, everybody. Welcome to episode 5 of AlgorithmsThread. I'm your host, David Harmeyer. Today we'll be talking about persistent data structures. They're a really cool modification you can make to other data structures, and it lets you basically go back in time and look at what they used to be. This kind of requires knowing segment trees, so if you're not familiar with segment trees, I recommend watching episode 3 first, where we talk about segment trees there. I'm not going to cover how they work in general, because that might bore some of the other people who are very familiar with it already. So the first problem I'd like to talk about is an ASC problem called persistent queue. And I'll link to this in the description of the video and in the Codeforces blog post. But in this problem, what you have is you've got like some queue, and initially the queue starts empty. And there are two things you might need to do to the queue. The first one is add some element, just like how you would add to a queue normally. And the next thing is like pop some element, like remove it from the front of the queue. So if this were the entire problem, and then after you pop the element, I guess you print what you popped. So if this were the entire problem, this would be a very, very simple problem. We would have no trouble doing it at all. We could just use some built-in queue and it would be easy. The issue though is that you also have to pass in what version of the queue you wanted to change for each of these. And that's what makes this a problem about like persistence. So what does this version thing mean? Initially you've got like some queue, and this is, we'll call this version 1. And at version 1 the queue is just empty. I guess just like that. Then on the second step, what we can do is we can make some modification to this, and this will create the version 2 queue. So maybe we add like an A to the queue. So now we have a queue that just has an A in it. And now in version 3, maybe we make it off version 2, and this version 3, maybe we add a B to the queue. So now we have this AB. And maybe in version 4, what we do is we look from version 3. This will be like a plus B. And maybe in version 4, what we'll do is we will, maybe we'll pop. So that'll remove A from the queue. So now we'll just have this B, and then we print A in our output. So far, all we've been doing is just operations to a normal queue. But let's make it a bit more interesting. Maybe version 5 will follow version 3 here. And maybe version 5 will add, maybe it'll add like C. So then version 5 will be A, B, C. And this is no longer just like something we can easily keep track of with a queue, because in version 3 we might not have stored what that was. And like we'll have kind of like two different branching versions of this queue. It's not as obvious how we might represent it. This general idea though, although this isn't kind of the same thing you use for persistent segment trees, this is the same idea of persistent data structures. So what you can do is you can look at some previous version of your data structure, and then you can modify it in some way to create some new version. And you can just jump around between versions whenever you feel like, and that lets you do a bunch of stuff that you might not be able to do otherwise. Okay, so here's this persistent queue problem. Hopefully we understand what the problem is. If not, you can go read the formal statement in the description. Let's go over the solution to it. So I'm going to draw this in a slightly different way. What I'm going to draw is instead I'll have like some node here. And this will be the queue at version 0. So this is going to be like V0. And now when we add something to it, we'll add this node here. Maybe this is going to be, we add some A. Now this will be V1. And now maybe in V2 we add a B. This is V2. So each of these versions have, I guess, two different pointers. The first pointer will be to the node that is the front of their queue. Or I guess the back of their queue, like the end of the queue. And the second pointer is where the queue ends. So this version 1 queue, it's represented by just an A. And in this tree, what we can do is we can store it as some path in the tree. So this path from A will be like this inclusive all the way to excluding this node here. The version 0 queue doesn't include this node at all, so it's like this node up until not including that node, so it's just empty. This version 2 queue, what it should be is it should be A and a B. And we can represent that by keeping track of the B is the bottom of the queue, and then the top of the queue will be this node right here. So the queue will look like that. It'll be the A followed by the B. Let's do a couple more additions to the tree so we get a more complicated tree, and then we can see how it will change. So maybe the next thing we do is we look at version 1. Oops, we look at version 1 and we want to add a C to version 1. So if we do that, we'll add some C node here. Now this will be version 3. Now maybe to version 2 we add like a D. So we'll create a D node and then add it to version 3 or version 2, and then we have version 4. All right, cool. So now maybe what we want to do is we want to take version 2 and we want to remove one element from it. Now that'll create version 5. So what will version 5 be? Well, we'll have this v5. The tail will still be this b, but the head will be whatever version 2's like top of the queue was, and we need to go down one from that. So that'll give us this a. And we can go down just one node by, well, we know the distance between these two nodes here. And we can do binary lifting from this node to go up that many steps. So if the total number of steps here is n, we need to go n minus 1 steps up from b using binary lifting. And we can do that in log time. So we can remove from that, and then we can see, all right, the top of version 5 will be this a here. And we can, since we found the new top, we know that the element that we just removed from the queue was this a. So we can do that. We can print that in standard output. Okay, so yeah, that's the idea behind persistent queues. Basically, the whole thing just turns into a tree, and you just do different things on a tree, and you have to build the tree as you process the queries. You can do all of those queries online, and it's, I guess, very helpful. So if you're interested in that, I recommend just solving that problem. It's an Andrew Stankovich problem. It doesn't use standard input and output, which is a little bit annoying. You have to do like file input output, but it's a pretty easy problem as far as ASC sets go. Andrew Stankovich contest sets, that one's on the easier side. Awesome. So that was the persistent queue. That hasn't really come up ever for me other than that one problem, but it's useful as like a demonstration exercise. The next thing that comes up a ton, which is very helpful, is persistent segment trees. So how do those work? Well, here's the main idea. When you have some segment tree, initially you'll have a bunch of nodes in your segment tree. Maybe your segment tree looks like this. Actually, I guess I'll draw one more layer just so we have a good example. Usually I draw segment trees in a slightly different way, but I think this is more helpful for the example I'm going to give now. What we want to do is every time we change part of the segment tree, we want to get an entirely new copy of the segment tree. That's the goal. And then we'll store all of these copies of the segment tree. And when we're done, what we can do is we can just look at any particular copy and we can see stuff about that copy. So we can like access the segment tree, what it used to be 20 steps ago. All right, so we have the segment tree. And initially this is what the segment tree looks like. And now maybe we change this node here, for instance. When we change the segment tree node, all of these segment tree nodes might change. So let's say we get a new version of the segment tree. And what that'll be is it'll be like pretty much the same segment tree, but we'll copy a bunch of nodes. So it'll look something like this. All right, so this is the new segment tree, but there's kind of an interesting thing that we've done here that we didn't really have to do. These nodes right here, it's possible that all of these nodes changed. But we know, because of like how segment trees work, that all of these nodes are all going to be the same, because we didn't modify any of them. So there's not really any reason for us to copy this whole giant tree when the only nodes that actually could have changed are these red ones here. So what we can do is, instead of creating all of these extra nodes, we can just do this. This left pointer, instead of going to this new thing we have to create, can just go to this old subtree right here, and then this part of the tree can just go to this subtree right here. And then I guess this also has to go to this subtree. So it's I guess a little messy. But the idea is most of the tree doesn't change every time we do some operation. So every time we do some segment tree query, we only hit log different nodes. And it's possible that all of those nodes change. But all of the nodes that we don't visit, or all the nodes that we break early from without changing their propagation values and stuff like that, those nodes are all going to be the same. Which means we don't have to go through the whole process of copying all of those nodes if we want a new copy of the segment tree. Okay, so that's the general idea. How do you actually implement this? Well, it turns out that it's you got to be a little bit careful, especially if you have lazy propagation, but it's not that bad. The main important thing to keep in mind is, like, every time you call some method on a segment tree, like every method will return the new node that represents it. So if you call like a range query operation, that might do some update to that node because something might propagate if you do a range query operation. So every time you do a range query operation, what that segment tree node has to return is it has to return the new version of the node. And it has to, like, construct a new node and then return that as it goes. So what's the runtime of these persistent segment trees? If we want to create a new version, we can do that in just like log n time every query. So it's going to be like log n per query. But we also have like another important like thing to keep in mind here, which is we also use log n memory per query. And sometimes that's an issue. There's not really a good way of getting around that with persistent segment trees other than finding a better solution that doesn't need persistent segment trees. But yeah, if you're going to use persistent data structures, every time you change it, you're going to need more memory for each node that you create. Same thing in that queue. We need one piece of memory for every version of the queue. So it's going to be order n memory, even if the maximum size of the queue is very small, because we have to keep all of the versions stored. Occasionally you can do like optimizations related to the problem to decrease this amount of memory, but that's not true in general, so I won't really talk about that too much. Okay, so that's kind of how you do updates to persistent segment trees. Let's look at some example, because I think that would be very helpful. So the example that I have prepared is, let's say you have some array, and it's just a bunch of elements. And what you want to do is you want to answer a bunch of queries where each query is of the form you're given some L and some R. And you want to say, if you sorted this array, this subsegment, what would be the kth largest thing if you sorted this? Now you can do this with wavelet trees, also in nlogn, and that would work as well. But we're going to use persistent segment trees instead, because I think they're more applicable to other problems where wavelet trees don't quite work. Also, wavelet trees have a massive massive constant factor. Persistent segment trees have a pretty big constant factor, but it's not quite as bad as wavelet trees. So yeah, so we want to find the kth largest thing if we sorted all of these numbers. Those are all of our queries. So our bounds will be like n is less than or equal to 10 to the 5th, and the number of queries is also less than or equal to 10 to the 5th. Now, it should be pretty clear that if we actually just went through all of these elements and tried to sort them naively, that would be like n log n. We could do quick select because we only care about the kth largest. So we could do it in order n. But still, that would be like n times q, that'd be 10 to the 10th, too slow. Not gonna work. All right, so instead, how do we do this? Well, here's one thing we might do. We can, I'm gonna go over two solutions. The first one is like slightly suboptimal, but it's easier for me to think about. The next one is faster and like it saves a log factor, so it's quite good. So let's say we have some elements. Maybe we have like this one here, 2, 3, 4, 8, 3. So maybe this is our array. Oh, let's add some more, I guess. 5, 9. Okay. So now we have this array, and what we can do is if we have our persistent segment tree, we can imagine adding the numbers in from smallest to biggest. So over time, here's what our segment tree will look like. At the end, this is what our final segment tree will be. But right before that, we'll have a segment tree that looks like this. Right before that, we'll have a segment tree that looks like this, then this, then this, then this, then this, then this. So what you can imagine I'm doing is I'm just going to like use Control Z to go back in time here. But what we can do is we can, just by looking at a different segment tree in our list of all of the versions of the segment tree, we can slowly go back in time like this and go forward in time. And as we change which version we're looking at, we can change which elements are there. So in order 1, we can change from this segment tree to this segment tree. And we can take any number of steps forward and backward. We can delete any number of numbers. So what we can do then is we can look at this range, and we can binary search how far back we need to go in order for half of the numbers in this range to be like contained. So maybe we go like 3 steps back, and now we're like, okay, well, we've taken too many steps back in time, because if we take 3 steps back, then there's only 1 number in the range, and we need there to be 2 numbers. So maybe we take 1 step back, and now we're like, okay, 1 step back is fine. So we need to take at least 1 step back and less than 3 steps. So it's either 1 or 2 steps. So now we try taking 2 steps back, and we're like, okay, that's also fine. So now we've taken 2 steps back, and we've seen the element that we added, or I guess, yeah, the element we've added is going to be this 8. So that's the second largest element in the range. So basically what you can do here is you can binary search like the answer, I guess. And then if you know what the answer is, then you can remove all of the things smaller than it and check if it's too big or too small. We wouldn't be able to do this with a normal segment tree. The reason we can't is because to shift between these 2 positions, we might need to remove a whole bunch of things from our segment tree. And if we need to remove a whole bunch of things, like we might need to remove half of the things, that's going to be order n, just to do that one binary search check. So that's why you would need persistent segment trees if you're going down this line of thinking. All right, so that's one solution. Every time, so initially we'll have like this n log n pre-comp. And then after that, we have a bunch of queries. So for each query, we're going to do a binary search. That's going to be log n. And then we're also going to do a segment tree query inside that binary search. That's going to be another log n. So the final runtime here is going to be like q log squared. That's going to be this little part. All right, so that's well, let's keep our array. That's going to be one way of solving it. The second way of solving it is also pretty interesting. And it lets us save a log factor. It lets us get a solution that's just n log n instead of n log squared. So how do we do that? Well, instead of keeping a segment tree over all of these positions, what we're going to do is we're going to keep a segment tree over all of the values. So we're going to like have some segment tree that'll answer the question, how many numbers? How many numbers are like less than or equal to some integer x? And we can pass this x in, and in log time, the segment tree will tell us, okay, there are 10 numbers less than or equal to x. So the first thing we'll do, obviously, is coordinate compress. Once we've coordinate compressed, we have order n numbers. Now we can do our segment tree and do some stuff on that. But the issue is, what we're going to need to do is, in order to figure out how many numbers are less than or equal to a certain value, we're going to need to, like, let's say we want to see how many numbers in this range are less than or equal to 5. Well, what the answer for that is going to be is it's going to be how many numbers in this first range are less than or equal to 5, and also how many numbers in this range here are less than or equal to 5. And if we know both of those values, then we can subtract them and get this answer for the range we're interested in. So in order to do that, what we'll do is we'll store a bunch of segment trees. Each of the segment trees will answer this type of query. But the first segment tree will just be of only the first number. The second segment tree will be of the first 2 numbers. The third segment tree will be of the first 3 numbers. So now we'll have n different segment trees. And each segment tree is pretty much the same as the previous one. It only differs in log n different nodes. So we have all of these blue segment trees here. And now what we can do is we can also solve it in log squared. We can binary search the answer, and then to check a given answer, we need to query, so for this range here, we're going to query this segment tree and this segment tree. We're going to look at both of them, and we're going to say how many elements in this first thing are less than or equal to whatever our binary search value is, maybe it's 5, and then same thing here, how many are less than or equal to 5. And when we do that, we can find out the difference of those is going to be how many elements in this range that we're interested in are less than or equal to 5. Okay, so that works. That's, again, an n log squared. We can optimize that, though. We can make it a little bit better. And the way we can do that is we have these 2 different segment trees. Instead of like doing a certain cutoff value and saying, figure out how many are less than this value, how many are bigger than this value, the way these segment trees are going to work is they're going to have like a list of values, right? So each of these segment trees will be like, conceptually, it'll be some array. And we'll store how many things are equal to 0. So maybe we've got like 1 thing equal to 0, how many things are equal to 1, maybe 2 things are equal to 1, 2, 3, 4, 5, etc. So maybe like 0 things are equal to 2 and 3, 1, 4, and then 1, 5. So if you want to know how many things are less than or equal to 5, there might be a lot of 6 here, maybe there are 3 6s. What you want is you want to range sum on this segment tree. But now what we want to do is we want to find the 5th thing in this segment tree. So our 5th is a bad example. Maybe we just want the 4th thing. So we're looking for this 4. That's the question we're trying to answer, right? What's the 4th thing in this prefix? So if we have just like, if we're answering some prefix, then we only have to look at one of these segment trees. We can handle that pretty easily by walking down the segment tree. And we can see, okay, we need to find the 4th thing in this segment tree node. We can see how big is the left child and how big is the right child. And now we can figure out, is the answer going to be in our left kid or is it going to be in our right kid? If it's in our left kid, we can just go down our left kid and then find the 4th thing. But if it's in the right kid and the left kid has, maybe this is how it's split up. So this is your left kid here. This is your right kid here. I guess we'll make it those 4. That's not how a segment tree would usually divide, but that's fine. So yeah, okay. So this is the left kid, that's the right kid. We're looking for the 4th thing, which is right here. So this node here has 3 elements. And we want to find the 4th, which means we want to find the first smallest element in this right kid. And that's the idea. So we can just walk down the segment tree. We can see, okay, is our answer going to be in our left kid or our right kid? And what index do we need to look in that particular kid? We can do a similar thing when we're not looking for the prefix as well. So here, that observation was we're just looking down one segment tree. If we're looking down 2 segment trees at the same time, we can actually use that same optimization. We can just see really the number of things in this left kid are going to be like this bigger segment tree's left kid minus the smaller segment tree's left kid, because we're only interested in the difference, and that's what will change in this range right here. Okay, so yeah, that's how you solve this problem. And then you can, each time you answer one of these queries, you can pick the 2 persistent segment trees, the 2 copies of the segment tree that you're interested in. You can walk down both of them at the same time, and then you can answer the query in log time. All right, there's one more problem I'd like to go over with persistent segment trees, and I will link to this in the description as well. This problem is kind of similar to the last one. In this problem, you're given some tree, and it's not necessarily a binary tree. It can be any tree. Mine might wind up, yeah, there you go. Now it's not a binary tree. Yeah, it's not necessarily rooted either. It's just like some general tree. Cool, now we have a good tree. And what's going to happen is we're going to be given, well, the tree has n nodes, first of all, which is less than or equal to 10 to the 5th, as usual. And you also have to answer a bunch of queries. So the queries are, again, less than or equal to 10 to the 5th. So you have to answer lots of queries. And each query is going to be of the form. We're going to give you 2 nodes. Here's your first node, and maybe here's your second node. And what you're going to do is you're going to look on the path between these 2 nodes. There's only one path because it's a tree. And you have to tell me what's the kth largest element on this path. So this is a similar problem. You can imagine that if you could solve this problem, you could also solve the first problem. Because if you can find the kth largest on a path, then you could do a similar thing with kth largest on some array. Because you could just have a rope, and then you could answer a bunch of queries, but each query is on the rope. So this is pretty much the same problem, except this problem's on a tree. Well, how do you do it? Let's add another node here as like the parent. Maybe this parent has some other kids. So again, we could use the first solution idea that I talked about, which is we could have this entire tree, and we could add nodes to the tree in one by one, and we'll add them like from smallest to biggest. So maybe we add this one in here. Maybe this is the smallest node, so we'll mark that one. This is the next smallest node. Then this node. Then this node maybe, then this node, then this node, then this node, then this, then this. Yeah, I'll just fill them in some order here. And by using persistence, what we can do is we can go back in time, and we can jump between versions where we have different numbers of nodes added in at a time. And we can binary search how many nodes we want to be added in. And when we binary search this, we can figure out whether there are too many or too few on this path. So just to elaborate, how do we check how many are on the path? Well, the number on the path, we can keep track of, So if we have some Euler tour of the tree, it's going to look like this. What we can do is for each node, we can consider like a positive and a negative version of that node. So the positive version will be the first time we hit the node. The negative version will be the last time we hit the node. And here's the important thing. We can get the LCA, least common ancestor, lowest common ancestor, I guess, between 2 nodes in log time with binary lifting, or we can use an ARMQ, get it in order 1. And then what we can do is we want to answer 2 different queries. So our query is going to be from this node here to this, from the LCA to one of the nodes. We want to answer that query. We also want to answer from the LCA to the other node. What we can do in order to do this is we can, every time we mark a node, we can add a positive one to the left side of the node and a negative one to the right side of the node. So this node will have a +1 and a -1 here. Then we'll have a +1 here and a -1 here. +1 here, -1 here. Plus, minus, plus, minus. Plus for this node here, minus, plus, minus, etc. So we have all of these pluses and the minuses as well. When we do a range sum on this Euler tour path, so a range sum on the green path, we'll find a range sum from the LCA to this query node here. And we'll find that range sum. When we do that, that will include pluses for all of the nodes that we entered but didn't leave. So this node here won't get counted because it has a +1 and also a -1. but this first node here will, because it only has the +1. This node will get counted, and this node will get counted. So we can count how many nodes are marked in some path on a tree like this by doing just a range sum on a segment of some array. And the array will be the nodes sorted in this order, marking the first time you enter the node and the last time you leave the node. So then to change which nodes are marked, when we, like, let's say for this node here, we want to, like, we just mark it. When we mark it, we add a +1 here and a -1 here. So then we can binary search which version of this tree we're on, and we can see in this version how many nodes are marked along the path. We also know how long the path is. And by seeing how many nodes are marked and how long the path is, we can really easily figure out, do we need to go forward in time or backwards in time? Okay, so that's the first version of a solution here that'll run in n-log². And the problem I'm going to link in the description, the time limit is very tight, so this won't pass. We can do a very similar thing though to the other solution, which is we can keep a persistent segment tree, and that segment tree will store the same thing. It'll store how many nodes that we've seen are less than or equal to x. So let's write that down. And if we can answer this question effectively, then we can do a similar thing. So let's say we had some segment tree that represented the nodes on this path, and some other segment tree that represented the nodes on this path. And I guess some third segment tree that represented the nodes along just this path. So if we have, oh sorry, this should be this path here. Okay. So if we have these trees, what we can do is we can figure out how many nodes are less than or equal to, like, 5, for instance, by saying how many nodes on this first path are less than or equal to 5, how many nodes on the path to the other node are less than or equal to 5, and then we need to subtract out how many nodes on the path above this root are less than or equal to 5, and then also we may have counted the root twice, so we have to be careful with that. And we can do that, and we can binary search the answer. Again, we have a log² solution. Now, just like the last problem, we can also walk down these segment trees in the same way. You have to be really careful here, because at this point you're walking down either, it depends how you implement it, but either 3 or 4 different segment trees at the same time. So it's very detail oriented, and I'm not going to go through all the details because it would be boring and kind of unhelpful. But you can kind of see how it would work. So if you manage to get these segment trees, then you can walk down them in a pretty effective way by saying, okay, do we need our answer to be bigger or smaller than this value? And we can decide whether we want to go down the right child for all segment trees or the left child for all segment trees by saying, if we look at these 4 segment trees, is the total with, like, adding this, subtracting this, is that total going to be too big or too small? Cool. Yeah, so that's this problem. The one detail I have left is how do we get these segment trees that I'm talking about? We can do that with just a DFS. So what we'll do is the nodes that are added to the segment tree will just be you and your ancestors. And we can keep that true as we walk down the segment tree. So we'll start off with nothing in the segment tree. Now we go to this node. Now this node adds himself to the segment tree. He goes down his left kid, and his left kid now has this version of the segment tree with all of his parents added. The left kid will add himself to the segment tree. And now this kid has, like, some version of a segment tree, and it's a full segment tree, but the only thing in it is this kid's, like, versions of the segment tree that contain this kid and his parents. Then this kid, or this root here, the root of the entire tree, will have its version of the segment tree that doesn't have all of its kids' stuff added to it. And this can look down its left or its right kid and give it that new version that doesn't have all of this junk added to it that it doesn't care about. And this can do the same thing. It'll look down this segment tree. It'll give some version of the segment tree for this subtree to take care of. And when it comes back to this segment tree that this node here has, this won't be changed because it's persistent, and every time this changes it, it creates an entirely new segment tree, and then can pass that version onto this group as well. So yeah, basically it's just a DFS. That's the TLDR on how do you get those segment trees. Then you can walk down them. All right, so I hope you enjoyed. This was persistent segment trees. There's a lot of really cool stuff you can do with them. And I think I'll link 1 or 2 additional problems that I didn't talk about in the description as well, if you're interested in some practice. That's all. Thanks for watching. Goodbye.